Many dielectric materials have an absorption feature in the UV that is not adequately described using the Cauchy material file. In this example, I'll show you how to fit for the optical properties of a UV absorbing film on silicon. I have data open, and the first thing I notice is that the film is transparent above about 400 nanometers. I know this because the oscillations are all about the same height. Below around 400 nanometers, they start to dampen off, and this is where the absorption feature is. When working with materials that are absorbing in one region or transparent in another, it's usually best to split the problem into two parts. So first we're going to work on the transparent region. To select this region, I can click with my mouse and drag. Alternately, I can choose Select Ranges from the data panel and specify wavelength range. I'm going to enter a minimum wavelength of 400 nanometers, and now I am going to build a model based on the assumption that this region is transparent. To get started, we need the blank model from the basic folder. We know that the substrate is silicon, so we can enter that in from the semiconductor folder. Choose SI_JAW. Now to model the film, there are a couple variations. If we have prior knowledge of what the material is, we could consider using some of the pre-built oscillator functions for a given material. You'll see there are several here. I'm going to assume that I have no information about this film and work exclusively with the B-spline for this example. With the B-spline layer entered for my film, I need to enter a starting thickness value. I'm going to guess 100 nanometers. Click Generate. 100 nanometers is too thin, and my starting value for index is also not quite right. I need to make adjustments here before I can do any fitting. I need starting values that are closer. So first I'm going to adjust the thickness, hold my mouse over the value, press Shift and scroll until the number of oscillations match. Now I have two sets of oscillations in my model generated data and two sets of oscillations in my experimental data. But the amplitude's still not correct, so I need to adjust the index. Hold my mouse on the index value, and this time press Shift and Control before scrolling so that we can scroll in smaller increments. As I move this up, you'll see the oscillations match an amplitude around 2.3. And then I need to go back and adjust the thickness. I'm going to scroll this back down to compensate for the change in index. So with a thickness around 160 nanometers and index around 2.3, this gives me starting values that closely resemble the experimental data, and I'm almost ready to do a fit. The last thing I need to do is turn on advanced options, and we're going to assume a transparent region. This is going to set the K values equal to 0 for this region. By default, it's going to let you specify a band gap, but if you prefer, you can turn this off and enter a region in nanometers, which is what I'm going to do here. So I'm going to enter a minimum value of 400 nanometers, maximum value of 1600 nanometers. This is the range that I'm working in now. I need to turn on the thickness as a fit parameter, right-click on the value, and then press Fit. Now I have a very good fit to the transparent region. I have a thickness. If I right-click on the B-spline layer, choose Graph Layer Optical Constants, I can view the index results for this region. And again, notice K equals 0 because we have specified that this is a transparent region using this advanced option here. We know that that was a good assumption because we're able to get a very good fit to the data. Now that we have the transparent region figured out, we're going to expand this model into the UV. To do this, we're going to use the wavelength range expansion fit, which is found under Other Options. By default, you'll notice that the wavelength range expansion fit increment is 0.5 eV. What this means is it's going to add 0.5 eV range of the data that is outside the currently selected range. It's going to add 0.5 eV at a time and fit the data in small chunks. It's not critical, but we recommend that you set this value to match the B-spline resolution. That way you're adding in one node of the B-spline at a time. So I'm going to change this to match, set it at 0.3 eV. And since we're working in EV, you might want to change your view. To do that, go to the Options tab, select Wavelength Units, EV, and then go back to the Analysis tab. Alternately, you can press Alt-Control-W to toggle back and forth. So this is still the same range, just in EV, and we're ready to choose Wavelength Range Expansion Fit. So I'm going to click on this now, and it opens a new window where you can specify a limited range if you wanted to. By default, it's going to expand the fit over the entire measured range. Then you can see it's adding more and more UV data, 0.3 eV at a time, until it reaches the end of your measured data. If you wish, you can switch back to nanometers. Either way, we have a good fit to the data. Our thickness value is about the same as it should be because the film thickness doesn't change from the UV to transparent region. Right-click on the B-spline layer, graph layer optical constants to view the optical properties of this film. And this looks pretty typical for a dielectric material that has one absorption feature in the UV. If we want, we can turn on the KK mode. This will force the physical relationship between N and K through the Kramers-Kronig transform. After you do that, you do need to press Fit again. It'll make some slight adjustments to the N and K values so that that relationship is maintained, but overall the fit is the same. We still have a good fit to our sine delta data, the thickness is the same, and our optical properties match our expectations, and the fit is complete.